So good evening everyone to the week 8 discussion of this course social networks, and this course is taken by originally taken by Professor Sudarshan Iyengar, Professor and Head of the Department of Computer Science and Engineering of IIT Ropar. Myself Ayan Paul, I am a PMRF research scholar from IIT Kharagpur and I am a PMRF TA for this course. By TA, my duties are I will solve a few questions that will be very much similar to your assignment, so that whenever you will be solving the assignment you will not feel it's completely new. But before that I always prefer to discuss some of the topics that has been discussed in this week, so that it will be easier for us whenever we are tackling the questions. Okay, so let's start. So today we will be talking something about hubs and authorities. Okay, so what is this hubs and authorities? Okay, so social networks can be modeled as a directed graph. We have seen directed graph in the case of web graph, citation graph, etc. These are basically or even some of the social media graph like Twitter, Facebook, all are directed graph. That means uh, you may follow someone, but that does not imply that that person will also follow you. Unlike friendship network, those are undirected graph. That means if you are friend with someone, that someone is also friend with you. So those are directed graph, but those are undirected graph. Friendship network is a undirected graph. But here most of the web graphs like web graphs and social network graphs, citation graph, etc., these are directed graph. That means you may follow someone, but that does not imply that person will follow you. Okay, so these are directed graphs. So social network can be modeled as a directed graph. Nodes are here users, edges it represents follows or replies or mentions or interactions. Okay, so this is nodes and edges. You know, in a graph two things are important. One is nodes and another one is edges. Okay, so you have any web graph, any social network graph, if you are given, you have to find out first these two things: what are the nodes here and what are the edges over here. Okay, so there is a hits algorithm. What is hits? Hyperlink induced topic search. So this is the algorithm name. So can be applied to rank users based on the influence and connectivity. It assigns two scores. One is a hub score and another one is a authority score. Okay, so for that we have to understand what is hubs and what is authority. Okay, so let's start with what is authority. In simple terms, authority is someone considered important or influential in this network. Very simple. Someone who is considered important or influential in the network, this is known as authority. They are known as authorities. So a user is an authority if many strong hubs interacts with them. Very easy, like any popular influencer, those are authority. Okay, and hubs are all the followers. Those are following him, her. Okay, so this is authority. So characteristics in social network, authority has many followers, especially from users who themselves follow many others strong hubs. Okay, so authorities usually have many followers, and this followers also has other followers who are following them. Okay, so produces content that attracts attention, replies, or endorsement. Example, on Twitter, a celebrity or a domain expert who is widely followed by active users is known as authority. Computational in this hits algorithm, authority score is given by this sigma half score of u. Okay, where u follows v. Okay, so what we need to know, we need to find out authority score of v. To find out authority score of v, we will do the sigma half score of u. What is u? You are the followers of v. So this is authority. Now what is hubs? Hub, a user is a hub if they follow or connect to many authority users. Hubs are connectors or aggregators in the network. Characteristics in social network follows many influential users, acts as a curator or recommender, pointing attention towards authority. Okay, so again I am repeating, hubs, who are hubs? A user is a hub if they follow or connect to many authority users. So this authority users, many people are following them. Who are following them? These are nothing but hubs. So hub is actually following the authorities. Okay, so hubs are connectors or aggregators in the network. Okay, characteristics follows many influential users. So these hubs, they follow many influential users, act as a curator or recommender, pointing attention towards the authorities. Okay, so they are curator or recommender, because whenever they are uh, following any authority, they are actually recommending them to other of their own followers, or somebody some people they are influencing. Okay, so that is why act as a curator or recommender. Okay, pointing attention towards the authorities. On Twitter, a new aggregator or active community member who follows many experts, so he she can be called as hubs. So computational here, this formula is very same. Hub score of user u, that will be given by sigma authority score of v. Okay, so v followed by u. So here what we were calculating, we are calculating authority score of user v. V is the authority. Okay, and u here is a hub. Okay, so that will be given by sigma u follows v, hub score of u. Here it will be reverse. Whenever we are talking about hub score of user u, that will be given by sigma, where the v followed by u. Okay, because v will be followed by u, authority will be followed by hub, and authority score of v. So by that we can calculate the hub score of u. So important thing here is authority is dependent on hub. Hub is also one way dependent on authority. Okay, so role, hub, active community member, social network example, active community. If I talking about hub, active community member or curator. Authority, influencer, expert or celebrity. Behavior, hub follows many authoritative users. Authority follows many hubs. Produce valuable content. Okay, so hub, authority, hub votes for authorities following, interacting with them. Authority will be hub. Authority gain reputation when followed by strong hubs. So again I am repeating, hub follows authority, hubs vote for authorities following, interacting with them. Okay, authority will follow hub. Authorities gain reputation when followed by strong hubs. Okay, so hub will follow authority, and authority will gain reputation when it is followed by hubs. So there is a mutual reinforcement. The Head's algorithm iteratively updates hub and authority scores until the convergence happens. Okay, so this is the whole thing about hubs and authority. So two things we have followed. One is authority. We have followed in this presentation, or in this first slide of the presentation, what is hubs and what is hubs and what is authority. Okay, so first taking about authority. Authority is someone considered important or influential in a network, so that is authority. And hub a user is a hub if they follow or connect to many authority users. Simple. Okay, so in social media, authority can be influencer, expert or celebrity, whereas hubs are active community members or curator. Okay, this much you have to understand. And there is a mutual reinforcement among two. Okay, so this is the complete thing about hubs and authority. Now taking our discussion forward, what is the principle of repeated improvement? Okay, so principle states that a node's importance score. What is the principle of repeated improvement? So last slide we have discussed something about this mutual reinforcement. Okay, so this mutual reinforcement is what we are going to discuss here. So principle of repeated improvement. Okay, so there is a repeated improvement. So what this principle states, that a node's importance score, that is hub, authority or rank, is iteratively updated based on the scores of its neighbors, and through repeated iteration the scores gradually improve towards a stable, consistent ranking. Okay, so again I am repeating, a node's importance score. So a node can be both, right? A node can be hub, a node can be authority. Okay, is iteratively updated based on the score of its neighbors. Okay, so it is iteratively updated based on the scores of its neighbors, and through repeated iterations the score gradually improve towards a stable, consistent ranking. Okay, so very simple terms, what you understand is that hubs as well as authority, they have something importance. Okay, and we will reiteratively see that how their importance grow in a network. Okay, so a time will come when the due to this principle of repeated improvement, the rank will gradually improve towards a stable or consistent ranking. Okay, so that is known as principle of repeated improvement. Each iteration it reinforces influence. Being connected to important nodes increases your own score, which in turn helps others to improve their scores in next iteration. Okay, so this is the reinforce influence. Okay, so each iteration, we are talking about each iteration, we are not talking about single iteration. Okay, we are talking about iteration after iteration. Okay, so each iteration it reinforce influence. Okay, being connected to important node increase your own score, which in turns help others to improve their scores in the next iteration. So very well written. Now, this is something that has been taught to you in the slides in the weeks, so you can just discuss. But this is what principle of repeated improvement is. So now we will discuss the principle of repeated improvement in two cases. One is the social network, that is hits, and second is web search, that is PageRank. So in social networks or hits, what is hits? Hits is this hyper-induced topic search. Hits. Okay. So first I'll talk about hits. So it hits hub score updated as the sum of authority scores of user you follow. That is the hub score. Authority scores updated as the sum of hub scores of users who follow it. This are nothing but these two equation. Okay. So authority score will be dependent by sum of hub score. Hub score will be dependent by sum of authority scores. Okay. So this is what has been written. Repeated improvement start with the initial hub and authority scores often 1. So we generally start whenever we are talking about here, we will start with hub or authority score. Initially we will score with will start with 1. That means we will give 1 to each nodes, whether it is a hub or it is a authority. Update score based on the neighbor's score. Normalized to prevent explosion and repeated multiple times that to scores so that scores stabilize. Okay, so again I am repeating, first we start with the initial hub and authority score, usually 1, then we update the score based on the neighbor's scores. Okay, and then normalization is important because there is actually no need of normalization, but normalization we do to prevent the explosion, because if the score being added again and again and again, what will happen, that score will be very big. Okay, so it will be very hard for us to tackle, so that is why we normalize and at last repeated multiple times so that the score stabilizes. Okay, so institution, how you can understand this, if you are a hub, you follow many strong authorities, your hub scores will improve, definitely it will improve. Those authorities scores then increases in the next iteration. Okay, eventually hubs and authority mutually reinforce each other. So that is how this hits algorithm or hits usually operate. Okay, now we will talk about this hubs and authority in the case of the PageRank. So PageRank computes global importance by repeatedly updating the rank of a page based on the ranks of pages linking to it. Okay, so PageRank we have studied, I think 6th or 7th class, I think 6th 7th. You can just open those slides again. So PageRank computes global importance by repeated updating the rank of a page based on the ranks of pages links to it. A repeated improvement mechanism initializes all page with equal rank. So if you talk about this hits or page rank, you can see initially what we are doing. We are initializing here we are initializing every hub and authority with same score, that is often 1. Here we are initializing all page with equal rank. Okay, so same thing. For each page we update the rank. Sum of weighted rank of in linking pages plus the damping factor. Okay, plus the damping factor. Repeated until converges to stationary distribution. So same thing. Here also after multiple iteration the scores of hub and authority stabilizes. Here also your page rank converges to a stationary distribution. So institution here, being linked from high ranked pages improves your rank. Similarly in case of this, okay, you can draw the similarity from here to here. Okay, so here if you are a hub and you are following many strong authorities, then it is improving your score. Similarly here also, being linked from high ranked pages improves your rank. That higher rank then contributes to other subsequent iteration. Here also those authorities scores are then increases in the next iteration. So same thing, and then eventually hubs and authority mutually reinforce each other. Here iterative updates propagates importance across the whole network. So you can see, you can draw the parallels among hits and the page rank. Okay, same thing, it initially starts with equal ranks for all the nodes or equal score for hubs and authorities. Then what will happen is, if a hub is connected to strong authority, it will increase its rank, and in the next iteration those authority score will also improve because hub score has improved. Here if a page is linked from high rank pages, then what would happen is it will increase its page rank. Okay, and then as the page rank of those pages increases, the higher rank then contributes to other subsequent iteration. So iterative updates propagates importance across the whole network. So this is known as principle of repeated improvement. Okay, so how is it is repeated improvement? First, the hubs are get powered because they are following strong authorities, and then the authorities get power because they are followed by strong hubs then. So and eventually the thing stabilizes. So this is principle of repeated improvement. Okay, so so first we have talked about hubs and authorities, and then how the hubs and authority scores update. So that is by the principle of repeated improvement. So we will then move to the next slide. What is the next slide? So next slide is PageRank Revisited, an example. Okay, so we will be revisiting our PageRank with an example. So consider a small web graph with 4 pages. A is linked to B and C, B is linked to D, C is linked to D, and D is linked to A. Okay, so transition idea, PageRank flow along the outgoing link. Okay, so PageRank, you have to keep in mind that PageRank flows along the outgoing link. Okay, so now how you can understand the previous thing, that is hubs and authorities in this case. So step 1, construct a transition matrix P. Okay, so transition matrix you have to construct it. So out degree normalization, each row distributes its rank equally to all the out links. Okay, so what is happening here? Let me name it as A B C D. Okay, so let me name it as A B C and D. Okay, and here also A B C D, A B C and D. Now how we will make this matrix? See A. What about A? A is following B as well as A is following C. So if A has initially rank 1, because hubs and authority we initially give rank 1, we give score 1. Okay, so let's say A has initially score 1, but A is distributing that 1 to B as well as C. So A cannot distribute its rank to A, so that is why A to A we have 0. But A is distributing to B as well as C. So that is why B and C will get half points. So half points here to B and half points here to C. And A to D, A is not distributing it to D. So that is why we will follow only the outgoing links. Okay. So that is why A is distributing to B, no. So that is why 0. So our A is over. Now B. B is distributing to D. Okay, so B has outgoing link D, so that is why B will only give score 1 to D. Similarly, C is also giving to D, so that is why C to D, and D to A. D is giving to A, so D to A. So that is how we construct the transition matrix. This matrix is also known as Markov matrix. Okay, the important property of this matrix is if we sum to the basically column. Okay, so if we sum each column we will get 1. Okay, so that is half plus half 1 here also 1, here also 1, here also 1. Okay, because initially all the A, B, C and D nodes has 1 point. So that is why 1 here, 1 here, 1 here and 1 here. Okay. So row, source page, column, the target page. Okay, so row is the source page and column is the target page. Okay, so that is why this is the column. That is why column is getting B and C is getting half and half. So example, row A has outlink B and C. So P to A and P to A and B. So P, how we write it? PAB. That means point we are giving from A to B. So that is half. Point we are giving from A to C. That is also half. So that is how we are writing it. I hope you understood it. Okay. And then how we will proceed? Introduce a damping vector. A damping factor t equals to 0.85 accounts for random jumps or teleportation. Okay. So this portion is the damping factor. Okay. This portion is usually the damping factor. So PageRank updated formula. This is the updated formula. So if n equals to 4, that is number of pages, we have 4. So 1 minus d by n, d is 0.85. So 1 minus d by n, that will give you 0.0375. Okay, this is the step 2. Now initialize the page rank. Okay, so initialize the page rank. Now we are initializing the page rank. Now how we are initializing at the first step? First step, if 1 is the total, then we are giving equal to A, B, C, D pages. That is why A get 0.25, B get 0.25, C get 0.25 and D get 0.25. This is our step 3. Now step 4, compute new page rank for each page using transition, matrix and the damping factor. Okay, so this we have to calculate for each pages for each iteration. Okay, now this is PR0, that means page rank at the 0th iteration. Now how we can get page rank for the 1 iteration? Let's take an example of D. So how to get page rank of first iteration for D? D has inlinks from B as well as C. Okay, D has inlinks from B as well as C. Okay, and D has outlink A. Okay, so D has inlink B and C, each contribute PR by out degree. Okay, so PR was 0.25 and divided by 1 because out degree was 1. Okay, out degree, D has out degree 1. So that is why 0.25 by 1. Okay, we are talking about this part. PRU by out degree U. So out degree of D here is 1. Okay, so that is why divided by 1. Okay, so 0.25 by 1. But we have to do the sigma. That is all the neighbors or all the inlinks. Okay, so D has inlinks, 2 inlinks, B as well as C. So B will get 0.25 by 1 and C will get 0.25 by 1. If we add up 0.25, 0.25, that will become 0.5. Okay, and then just apply that formula of this page rank. So that will be this 0.0375 this and 0.85, the 85 is nothing but the damping factor into this 0.5. So now the page rank of this D will be 0.4675. Similarly you can compute for A, B as well as C. Okay, after each iteration PR vector moves closer to the stationary distribution. Okay, now PageRank Revisited, conservation and convergence. Now we will talk about the convergence. Okay, now this is the convergence conservation property. Total page rank in the network is always 1. Okay, so anytime you just take the page rank, sum the all the page rank like A, B, C, D, you just sum up, you will get 1. So 0.25 plus 0.25 plus 0.25 plus 0.25, that will give you 1. Similarly in the first iteration also, if you will calculate, you will get the page rank equals to 1. So that is known as conservation property. Okay, this property is known as conservation property. Total page rank in the network always sums to 1. Ensured by, okay, just 1 minute. Yeah, okay, yeah. So ensured by transition matrix rows, stochastic rows sums to 1. So rows or column, it sums to 1. Okay, so this is the thing. And then damping factor redistribute remaining probability to all the nodes. Now there is another property known as convergence. Iterative updates eventually stabilizes all the page rank vector. So you can understand that after one iteration, your page rank will not stabilize. It initially started with 0.25 equal for all, but it will not stabilize for after one iteration, two iteration. But let's say for after five iteration or six iteration or maybe 10 iteration, it gets stabilized. After stabilize means, for example, 10 iteration you have a page rank for A B C D as x w x y z. Okay, now 11th iteration, if it is stabilizes, then 11th iteration also page rank for A B C D will be w x y z. Okay, so that is known as stabilization. Okay, so convergence, iterative updates eventually stabilizes the page rank vector, converged PR vector stationary distribution of the Markov chain. Why convergence happens? Because these three properties are important. Okay, this question might be also asked because it is stochastic. Okay, stochastic means row sums to 1, it is irreducible, and it is aperiodic matrix, unique stationary vector. Damping factor is usually less than 1, ensure irreducibility. Teleportation connects all the nodes. Okay, so this is an example. For example, this is the first iteration, 0 iteration here, 0.25. Now after the first iteration, these are the page rank. This 0.25, 0.25, 0.25, here it is 0.4625. Okay, then in the next iteration, it is 0.431, 0.134, 0.134, 0.462. This is the third iteration. Okay, so you can see what is the page rank after each iteration. Observe PRD converges quickly because it has many inlinks from other pages. So PRD usually converges. You can see this. Okay, this usually converges. 4.46 to 5.462, 0.462. Okay, so this actually converges after two iteration. Okay, because it has many inlinks from other pages. Iteration continues until we change less than sigma, very small threshold. Okay, so key insight here: page rank uses repeated improvement principle. Scores propagate through the network iteratively, and eventually a stable global ranking emerges. Okay, so this is the thing. Page rank. This is the uh, uh, this is the page rank. You can see this is another example. So here this is the network. Okay, A, B, C and D. Okay, so you can see here A is following C, C is following B, and B is following C, and then B is following A. Okay, so initially the page rank was 1 by 3, 1 by 3, 1 by 3. After the this is the 0th iteration. You can say after the first iteration it is 1 by 6, 1 by 3, 1 by 3, 1 by 2, and then this is the third iteration. So similarly you can solve the page rank. Okay, and after many iteration you can see the page rank actually stabilizes to 0.2, 0.4 and 0.4. Okay, that means after many iteration what will happen, the page rank will initially stabilizes and it will not change from 0.2, 0.4 and 0.4. Okay, so that is the stabilization. So this is regarding stabilization of the page rank, why page rank stabilizes. Okay, now to understand in detail why page rank stabilizes, you have to take the help of this first prerequisite, and two prerequisite is there. One is convergence in repeated matrix multiplication, and second is vector addition. Okay, so first is convergence and repeated matrix multiplication. So concept here, let P be a stochastic transition matrix representing a network where page users form replies. Let V naught be the initial vector scores, page rank vector, hits, hub authority vector or item score. So iterative process, this is the iterative process. So the Vk plus 1 vector will be equal to P into Vk vector. P is the matrix and Vk is the vector. Okay, so Vk plus 1 vector will be given by P matrix into Vk vector. Okay, so again I am repeating, P be a stochastic transition matrix. Okay, whatever we have, what is stochastic matrix, like rows or column, it's usually sums to 1. Okay, so P is that matrix, and V naught be an initial vector scores. Okay, Now iterative process, that is how, this is the simple multiplication, and then what we will do, we will do the what we will do the repeated multiplication propagates influence through the network, each iteration updates scores. Okay. Now why convergence happens, this is the main question that you have to understand. Okay, main question, why this convergence is happening. We are seeing that convergence is happening in PageRank or any other or like hits. Okay, but why this convergence is actually happening, that is the question. So first is stochastic matrix, each row sums to 1, that is the probability distribution. It is irreducible, every node can reach every other node eventually. And aperiodic, no strict cycle, so the influence does not oscillate. Okay, so there is no strict cycle, there is no cycle. Okay, that is why the influence does not oscillate. And last, that is the damping factor. In case of PageRank, it guarantees irreducibility even if disconnected graph. So result, after many iteration, what will happen, this vk we have started with this vk will converge to v star, that is the stationary vector. After that, the vector will not change. Context example, PageRank repeated multiplication of transition matrix by rank vector gives the stationary rank of page users. Hits algorithm, authority and half scores are updated iteratively via matrix multiplication until stabilization, and recommendation system also it is given, so you can see it. So what is the institution? So influence flows through the network and repeated updates gradually improves the accuracy of node scores and essence of the principle of repeated improvement. So this is important, principle of repeated improvement. So everything is happening because of principle of repeated improvement. So what we are going to say, let's say this is a matrix, if we are multiplying with this a vector, okay, then you will get a new vector. Okay, this vector let's say it is vk. So after multiplying with this p matrix, we are getting another vector vk plus 1. What we have to do, we have to just do the normalization, because it won't explode. That is why normalization is important. Normalization very easy, 3 by root over this square plus this square. Okay, so 3 by root over 3 square plus 7 square. Okay, similarly 7 by root over 3 square plus 7 square. So after normalization we are doing this. Now we will what we are getting, we will again multiply with this matrix, then again we will get this, and again we will do the normalization, and what will happen is eventually this thing will converge. Okay, now what is important is this matrix can be considered as your stochastic transition matrix, and this can be considered as your PageRank or halves or authority scores. You know, after many iteration, what will happen is this halves or authority score will converge, or this PageRank will converge. So this is the main concept. Now we have this another prerequisite, that is addition of two vector. Vector addition used to combine contribution from the multiple sources. Okay, so that is vector addition. So in network ranking, hits update authoritative scores, sum of the hub score, and all neighbor hub score, sum of authority scores. This is literally adding of two vector. Similarly, PageRank or teleportation damping, PageRank is this. So we are adding this. Okay, the second term, this is the second term, that is the teleportation vector is added every page vector component and shows reducibility or probability conservation. And recommendation system I am not discussing, you can see it. So key idea, vector addition ensures multiple influences are aggregated correctly at each iteration. Without addition, a node could only be consider one neighbor at a time, which breaks the ranking computation. Okay, so combined picture, if I combine the two picture, like prerequisite one, that is convergence and repeated matrix multiplication, and addition of two vector, what we will understand is first we will multiply matrix into the vector and it propagates scores through the network, and second we will add contribution from multiple neighbors or teleportation to aggregate the influence. And step 3, repeated step and 1 and 2, it scores gradually converges to a stable ranking. Okay, so this is the thing. Okay, so repeated matrix multiplication, you can just read it. Vector addition, it propagates score along the network edges iteratively, leads to convergence to stable ranking. And vector addition, it aggregates contribution from multiple neighbors, ensure cumulative influences captured. Okay, So we have two requisite. First requisite, we multiply a matrix with a vector and multiply repeated to convergence. And second is important addition of two vectors. If a big vector is added to a small vector, the resultant that we got, it will be closer to big vector, okay, both in direction as well as magnitude, okay. So this is the two prerequisite, okay. So this is important. If small vector, we are here addition of two vector, but addition of two vector, important thing is if we are adding a small vector with a big vector, okay, then you will get a resultant, okay. Resultant means the answer, okay. Now the resultant that you will get, and that will be that resultant will be closer to the that resultant will be closer to the big vector, both in magnitude as well as direction, okay. So both together are mathematical backbone for principle of repeated improvement, okay. So this is the thing, that is why two prerequisite is given. First is convergence and repeated matrix multiplication, and second prerequisite is addition of the two vectors, okay. Now let's move on to the next thing, that is explanation of the prerequisite. So key observation, no matter what vector we choose, repeated multiplication by a matrix eventually lands in the same vector direction, okay. So when you repeatedly multiply a matrix A with vector V, after many iteration, the result points mostly to the direction of the dominant eigenvector, okay. So this is the basis of convergence of iterative ranking like PageRank or heads. So actually the direction after many repeated multiplication, the direction that the vector is taking, that direction will be eigenvector of the matrix, okay, eigenvector of the dominant, okay. That is why in addition of two vector, I have told you the result will be dependent both in direction as well as magnitude. That will be dependent much on the bigger vector than the smaller vector. That is why here it will be dependent more on the dominant eigenvector of A. So this is the basis of convergence in iterative ranking. So intuition, direction stabilizes, converges even if magnitude keeps changing. For ranking, we normalize vectors to focus on direction, okay, relative importance rather than absolute magnitude. So magnitude we don't we don't care much. We care about the direction. That is why we generally go with the normalization. And then is recalling eigenvector and eigenvalues. So eigenvector and eigenvalue, you all know what is eigenvector. To get a eigenvector of a matrix A, you just multiply it with the vector that will be equal to lambda into V, okay. So A into V will be lambda into V, and what is this V? V is the eigenvector of this A, okay, and lambda is the eigenvalues, okay. So A into V will give you lambda into V. A is the matrix, V is its eigenvector, lambda is the eigenvalue of the eigenvalues of the A matrix, okay. So V is a vector whose direction does not change when multiplied by matrix A. So this is the definition of eigenvector, okay. A vector whose direction does not change when it is multiplied by a matrix A. So that matrix is the vector is the eigenvector of this matrix, okay. So eigenvalue, the factor by which eigenvector is scaled, okay. Only direction is not changing, because here also V direction, here also V direction, but its magnitude is scaled by some value. That value is known as eigenvalue. So any vector can be expressed as a linear combination of the eigenvectors, okay. So this V can be written as alpha V1 plus beta V2 plus dot 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 dot, okay. So that is how we can write it, okay. Linear independent eigenvectors form a basis for the vector space. So this actually forms the basis. For example, V is your total vector, and that can be divided into V1 vector, V1 into alpha plus beta V2 plus gamma V3, etc., etc., okay. So this V vector can be broken by this. This V1, V2, V3 are nothing but is eigen vectors, okay. So this is the thing. For example, A is a 2 cross 2 matrix, so it will get 2 eigenvectors and 2 eigenvalues. For example, alpha and beta with the eigenvalue and V1, V2 with the eigenvector. Then V can be written as alpha into V1 plus beta into V2, like that, okay. So this is how. And then third thing you have to understand is repeated matrix multiplication. So what will happen is, now we got this A into V. Now what we will do is, we want to multiply this A vector, A matrix again and again. So what will happen is, this is AV, okay, after multiplying it, let's say k minus 1 time, it will be A k minus 1 V. And how it can be multiplied? Alpha lambda 1 into k, because lambda 1, you say lambda 1 is the first eigenvalue, so it is by lambda 1 into k into v1. V1 is the eigenvector. Similarly, lambda is the eigenvector, okay. So beta into lambda 2k v2, okay. So key insights in the terms of largest eigenvalue, lambda 1 dominates as k increases. So if we just increase the k, what will happen is, as this lambda 1 is dominating, okay, so that is why as this lambda 1 is increasing, then what will happen is, this k value is increasing and lambda 1 is greater than lambda 2, lambda 3, etc. Then what will happen is, this term will be very much bigger than all these terms, okay. So this term will actually dominate. The first eigenvalue or the largest eigenvalues will actually dominate, okay. For example, let's say lambda 1 equals to 3, lambda 2 equals to 2. So if we are talking about lambda 1 by lambda 2, so it is only 1.5. But after, if we just put 2 to the power 100 divided by 3 to the power 100, it will be almost 0. Okay, so that is how it depends. As we keep on every iteration we do, what will happen is, the largest eigenvalue, okay, that is 3 here, so 3 will be more influence on 2. So if we keep the largest eigenvalue in the denominator, after many iteration, what you will see that the ratio will be eventually 0. That means that is the power of the largest eigenvalue. This shows that the direction AKV, okay, is essentially aligned with the dominant eigenvector of V1, most independent of the initial vector. And then connection to the PageRank. So this is the PageRank formula. This is exactly repeated matrix multiplication plus addition over iteration. PRK converts to a dominant eigenvalue. Okay, so this is the PageRank. Okay, PRK. So it converges to a dominant eigenvalue and modifies transition matrix. Okay, this PT is the transition matrix and D is nothing but your damping factor. Okay, so let's ignore T, just PT, PRK. Okay, so PT is the matrix and PRK is the PageRank. So PRK we can consider it as vector, and that after repeated multiplication you can say this PRK plus 1 stabilizes, because it will have effect of only one eigenvector. Okay, so this is the thing about eigenvalue and eigenvector, principle of repeated multiplication and addition of vectors. Okay, so this is the whole thing, how we can explain the concept, why things are stabilizing over time. Okay, now PageRank as the matrix operation. This is our last topic. So you can see let's take an example. A follows B and D, B follows A, C and D, C follows B and D, and D follows A. So again, what I have told you, this rows are nothing but source, and this columns are nothing but target. Okay, so A, B, C, D. Okay, A, B, yeah, A, B, C and D. Okay, so this rows are nothing but the source, and this is nothing but the target. Okay, so we have 4 source and 4 target. Okay, now what we can see, A follows B and D. Now A follows B and D, that means A, if initially A has 1, okay, so it is dividing 1 to B as well as D. That means half it will give to B and half it will give to D, and other thing is 0. So A to A it is 0, but A to B it will be half, and A to C it will be again 0, and A to D it will be half. Okay, Similarly, let's say BACD. BACD, it will be uh, BACD. Okay, B. Now B is giving to C. Okay. B is giving to C, so that is why we have given this. Okay, 1, and then C, it is giving to B and D, half and half, and D, it is giving to A. Okay, so that is why D is half here and half here. Okay, so this is the thing. So again I am repeating, what is happening is A is giving to B and D, but B, let's say B, it is giving to C, A and D. C, A and B is giving to C. Okay, that is okay, and A and D. So A and D is not considered. Okay, okay, and C, it is giving to B and D. Okay, so I'm not discussing this. I think there's a problem here, but what will happen is B is given to A, C and D, so it will be 1 by 3, 1 by 3, 1 by 3, 1 by 3 here. C is given to B and D, that's so it will be half B and D. Okay, half here and half here, and D is given to A. D is given to A, then it will be D is giving to A, right? D is giving to A, so D will be 1 here. Okay, so that is how. So this matrix will be 0, 0.5, that means half, 0 and 0.5. Okay, sorry. Okay, and second row it will be A, C and D, that means 1 by 3. Let's take it 0.33. Okay, 0.33 B to A, B to C. B to C means B to B will be 0. B to C will be 0.33. And B to D will be B to D will be again 0.33. Okay, and then C to B to D, C means B and D, that means 0.5 and 0.5. So 0.5 here, 0.5 here. Okay, and 0 here and 0 here, and at last D to A. D to A means D will give 1 here and 0, 0 and 0. And when you sum to each row, that will be 1 here, 1 here, 1 here and 1 here. Okay, so that will be the transition matrix. Okay, so this is actually wrong, so I will change it. This is actually wrong, so this is how we will look at. Okay, so that is how we will look at. Okay, and then you can just understand it how it has been given, and after what will happen after convergence, this VA will be 19 by 100, VB 1 by 3, CVC 19 by 50 and VD 9 by 100. Okay, so that is how you have to understand it. Okay, so this is the thing. Yeah, this is the thing. A follows B, A follows B, A follows D. Okay, nice. Then B follows ACD, B follows ACD, B follows ACD, B follows A. No, B does not follow. Okay, so I think this is written wrong, so that is why this is the problem. Actually, follows A follows B and D. A follows B and D is right, and then B follows. B is actually following C. Okay, according to here, B is actually following C. That is why 1 here. Okay, and then B following C. Okay, and then C. What about C? C following C following A and C following C following B. Okay, so C following A and B. Okay, so that is why C following A and B, A and B, and last is D, D following D following D following D following B, as well as D following C, D following C and B, B and C. Okay, B and C. So this will be true. For this is the matrix. For this is the matrix. Okay, so I will just improve it. Okay, and after that what will happen, actually eventually it is converging. Okay, and then let me just erase it. Okay, let me just erase it. Okay, and then repeated multiplication will what will happen, the matrix actually converges to VA, that will give in 19 by 100, VB 1 by 3, VC 19 by 50, and VD 9 by 100. Okay, so repeated iteration, it converges to a stable ranking. Okay, so concept transition or Markov matrix, this is known as transition matrix or Markov matrix. So normalized adjacency matrix, rows or columns, actually the columns sums to 1. Then initial vector, uniform page rank assignment, iterative multiplication updates rank to VK plus 1 to PVK, and then convergence, repeated multiplication, dominant eigenvector leads to stationary distribution, eigenvalue 1 guarantees a stable page rank, and resulting page rank vector will score of each page relative importance based on the network links. Okay, so here it is VA is actually 0.19, VV 0.33, VC will be 0.38. Okay, and VD will be 0.09. So what is the most important page is here C. Okay, VC. Okay, and VC has VC outgoing link is AB, and AB and it is receiving from ingoing link is B as well as D. Okay, so here the most influential page is here C. Okay, so VC is the most influential player. Okay, so this is the thing. So this is the thing. So let me just erase this. Okay, actually this is right, just this is wrong. So I will redo it. Okay, B is actually C, C is AB, and D is BC. Okay, so this is the true. So after the class I will update it. So this is the page rank as a matrix operation. Okay, now let's move on to the question answer part. So hubs and authorities, topics on which it will be discussed: hubs and authorities, principle of repeated improvement, page rank revisited, convergence and repeated matrix multiplication, addition of two vectors, and page rank as a matrix operation. Okay, so case 1, a social media platform aims to rank users based on the influence user links structure, where edges represents the follows. Now theory hits, we have already do iterative updates, that also we know. Page rank algorithm we have seen again and again. Okay, and then what graph interpretation skill, how to compute how authority scores manually, how to identify users as hub versus authority, understanding the effect of graph structure, that is cycling, dangling nodes, and out degree distribution, and compare hits versus page rank. And practical implication, these are the practical implication: hubs, users who follow many influencers; authorities, influential users with many followers; page rank measures global influence regardless of who follows whom locally; and last, network design moderation helps identify the influences potential for recommendation or advertising target. Now let's move on to the question answer part. In the hits algorithm applied to a social media follow graph, what characteristics makes a user hub? Option A, having many followers, following many users. Option C, high page rank score, or option D, posting frequently. So answer here is option B, following many users. Okay, so option B is the correct answer, following many users. In hits, how is a node that points to many good authority on a social media. This corresponds to a user who follows many users, especially influential ones. Having many followers relate to authority, not hubness. Okay, and so option B is the correct answer. Let's move on to the next question. Which factor increases a user's authority scores in its algorithm? Option A, uh, being followed by users with high hub scores, following many users, being followed by users with high authority scores, having a high out degree. So factor increases a user's authority score. So authority score will be increases by high hub score. Okay, so being followed by users with many hub scores. So option A will be the correct answer. Okay. So a node's authority score increases when it is pointed to strong hubs. So option A is the correct answer. Now let's move on to the third question. In a following graph, for user A follows B and C, B follows D, C follows D and D follows A. After one hits iteration with initial score 1, what is the user's D authority scores before normalization? Okay, so before normalization we have to find out what is the what is the user's the authority score before normalization. Okay, so let's see how to proceed with that. So D, nodes pointing to D. Okay, nodes pointing to D are B as well as C. So we have to go with the ingoing links. Okay, so D, B follows D and C follows D. So node that are pointing to D, that are B as well as C. Okay, so B, initially B has half score 1 and C has half score 1. So authority score of D will be 1 plus 1, that will be 2. So 2 is the right answer over here. Now let's move on to the next question. Why might PageRank be preferred over hits for ranking social media influencers? It accounts for content quality, it converges faster in sparse graph, it considers global link structure, it is less computationally intense. Okay, so why PageRank preferred over hits? Okay, so PageRank is preferred over hits because it considers the global link structure. Okay, and second is it is less computationally computationally intensive. Okay, so option C as well as option D is the correct answer. Okay, so PageRank, it gives us a single stable score, uses entire network and avoids the query dependent nature of hits, making it more practical for large social networks. So option C as well as option D is the correct answer. Now let's move on to the next question or the last question of this case. In applying PageRank to a social media graph, which ensured convergence, a damping factor less than 1, a strongly connected graph, handling dangling nodes, or option D, uniform initial scores. Okay, so definitely a damping factor less than 1, it helps, and then is handling the dangling nodes. So option A as well as option C is the correct answer. So damping factor less than 1, it ensures the PageRank transition matrix is irreducible and aperiodic. Okay, irreducible and aperiodic, guaranteeing convergence to a unique stationary distribution. Handling dangling nodes, nodes with no outgoing edges, breaks the stochasticity. Redistributing their probability masses, example, uniformly preserved a valid Markov chain and ensures the convergence. Okay, so uniform initial scores, this is incorrect because PageRank converges from any initial distribution due to damping factor. Uniform initialization affect only convergence speed, not convergence itself. A strongly connected graph, that is also incorrect. Strongly connectivity is not necessary when damping is applied, since teleportation connects all node probabilistically, because teleportation we are doing this 1 minus dy n. So this is known as teleportation. So we are doing it with the help of dangling nodes to ensure that even if the graph is not strongly connected, it will converge. Okay, so option A as well as option C is the correct answer. Okay, so this is regarding the first case. Now let's move on to the next case, web search optimization. A search engine uses a hits and PageRank to rank web pages based on hyperlinks. Okay, so again hits, all this we have discussed. Okay, graph computational skill, so same thing. Okay, so let's move directly on the question and answer. In the hits algorithm, how are hub score updated? Sum of authority score of page pointed to. Sum of half score of page pointing to average of all pages score based on the page content. So option A is the correct answer. Sum of authority scores of page pointed to. Okay. So option A is the correct answer. Half score of a page, sum of authority score of a page pointing to authority score, sum of half score of a page pointing to. So option A is the correct answer. Now let's move on to the next question. Which scenario favor hits over page rank for web search, topic specific queries, large scale web graphs, graphs with clear hub authority structure, real time ranking needs. Okay, so here option A as well as option C is the correct answer, that is topic specific queries and graphs with clear hub authority scores. Okay, so hits is most effective when the query defines a focus subgraph. Okay, so that is why topic specific queries is important, and there is a strong separation between hub directories and authority, that is content pages. So option A as well as option C is the correct answer. So in a graph A to B, A follows B and C, B follows D, C follows D, and D follows A. What is the hub score of A after one hits iteration? Okay, so A we have to understand. So A is followed by D. Okay, A is followed by D. So that is the thing. So after one iteration, what is the hub is score? Okay, so after what is the half score after one iteration? Okay, so authority score will be given by sum of the half score. Okay, so A is following B and C, B is following D, C is following D, and D is following A. All halves equals to 1 and all authority will be equals to 1. So step 1, so we have to do the hub update. Okay, so first we will start with the authority. So how we will understand this? A single hits iteration, authority updated using old hub score, hub updated using updated authority score. So first we have to update the authority. Okay, so how we will update the authority? Authority A equals to hub D. Okay, because A is followed by D. Okay, so that is why first it will be 1. Authority B will be equal to hub A. Okay, authority B will be equal to hub A because A is following B. Then authority C is equal to hub A. Okay, so authority C also will be equal to hub A because A is following C. And last, authority D will be following B as well as C. So hub 1 plus hub 2, so it will be 2. Okay, so that is regarding the authority, but we have to find the hub score. Okay, hub score of A. Now hub score of A, now we will be going about outgoing link. Okay, authority is incoming. Okay, incoming, I am writing authority means incoming. Okay, and hub means outgoing. Okay, so now we have to do the outgoing. Now outgoing hub A will be B as well as A will be B. Okay, authority of B as well as C. Okay, so this two thing, authority of B as well as C. So what is the authority of B? Authority of B is actually 1, and authority of C is actually 1. So hub of A will be 1 plus 1, that is 2. Okay, so 2 will be the right answer before the normalization. Now let's move on to the next question. What ensure page rank conservation property? The transition matrix is row stochastic. The graph has no cycle. All pages have equal out degree. The damping factor is 1. So here it is A is the correct answer. The transition matrix is row stochastic. Okay. So PageRank models a Markov chain. A row stochastic matrix ensure each row or each column rather sums to 1, preserving total probability masses rank conservation. Okay. So option A is the correct one. Now last question of this, which matrix properties are critical for PageRank convergence? Stochasticity, irreducibility, aperiodicity, symmetry. So option A, B as well as C is the correct answer. Okay. So stochastic, it is valid probability transition, irreducible, every state reachable, and aperiodic, no cyclic trapping. So symmetry is not required. So A, B as well as C is the correct answer. So this we ended the case second. Now let's move on to the case third, that is academic citation network. An academic citation network ranks paper based on citation, treating citation as directed edges. Now theory, all these things, notes, it represent paper, directed edges, it represents citation. We have seen this. Now here we will be using the heads. Okay, authority, a paper cited by Stronghouse is considered as an authority. Practice, highly cited papers often have high authority. However, a paper that cites many authoritative papers, authoritative score, sum of half score of citing paper, half score, sum of authoritative scores of cited papers. Okay, so these are the things, and then page rank etc is given. So let's move on to the question. In a citation network, which paper is likely an authority using heads? Which paper is using authority? Okay, one citing many paper, one cited by many papers. So option B is the correct answer over here. So in hits, an authority is a note that is pointed by many good hubs. So in citation, influential papers are those frequently cited by others. So option B is the correct answer. Which factors affects a paper's page rank in a citation network? Numbers of citations received, citations from highly ranked papers, number of citation given. Option D, publication date. So here option A, that is number of citation received and citation from highly ranked paper. This two will be important. Okay, number of citation received and citation from highly ranked paper. So option A as well as option B is correct. Okay. Option C is incorrect because affects number of citations given. So affects others page rank, not its own. Publication date not directly used in page rank. So a paper's page rank increases when a paper receives more citations. Those citations come from important high rank papers. So option A as well as option B is the correct answer. Let's move on to the next question. Okay. So in a citation network, A cites B, B cites D, C cites D, and D cites A with damping factor 0.85. What is the page rank of D up to 3 decimal place? Okay, so how we will calculate this? So let me show you how we will calculate this. So first you have to write the network. That is the first thing. Okay, so A follows BC, B follows D, C follows D, or D follows A. By follow I mean citing. Okay, A is citing BC, B is citing D, C is citing D, and D is citing A. So N is 4 here, and damping factor we are given 0.85. Okay, so teleportation, so damping factor has two networks. Okay, so first this is the thing, that is 1 minus D by N, and second is D into this pi, D into this thing. Okay, let me show you where it is given here. Okay, so let me show you here. Yeah, this thing. Okay, so first is this is known as teleportation, and this is the main page rank. Okay, so 1 minus D by N we will calculate, and that is 1 minus 0.85 divided by N is 4. Okay, so this we will calculate, and second is D, that is 0.85 into this. Okay, PRU by out degree. Okay, so that we will calculate it. So how we will calculate it? Yeah, so how we'll calculate it? So pi A, pi B, pi C, and pi D with page rank scores. Okay, so first we will be talking about A. So A is followed by D. So we will be talking about the incoming link. So A is followed by D. Okay, so that is why 0.85 into pi D. Now what about B? For B, B is getting from A but divided by 2, because actually the A rank is distributed in 2, B as well as C. That is why pi A by 2. Pi C again pi A by 2, and pi D. Pi D it is giving pi D, it is getting from pi B as well as pi C. Okay, so by that we can calculate the page ranks. Okay, so this is the how we calculate the page rank. Now we have to solve the equation. How we will solve this equation? This is, let's say this is the equation number 1, and this is the equation number 2. Now in this equation, what you have to do? You have to this equation, these two equations are same. So that is why pi b equals to pi c. So let's take pi b equals to pi c. So here pi b plus pi b, that is 2 pi b. Okay, so here 2 pi b, but this pi b is relating to pi a. So pi actually what will happen is let me yeah, this will be 0.425 pi plus 0.0375. So pi b minus 0.0375 divided by 0.425 will be pi a. Okay, or pi b will be equal to 0.0375 plus 0.425 pi a. Okay, so that we will just put here, and we will have two equation, one pi a of pi d. From that we can solve the pi d. This two equation we have two variables, pi a and pi d, and pi b and pi c we are replacing with pi a. Okay, so by that we can get what is the pi d. Okay, so pi d is coming 0.333, so 3326, so 0.333 is the answer. Okay, now let's move on to the next question. Why might hits identify different authorities than PageRank in a citation network? So here the answer is option B. Hits focus on a subgraph of relevant pages. Okay, so hits is a query dependent and works on a focus subgraph. Okay, whereas PageRank is global, often producing different authority rankings. Okay, so option B is the correct answer. Question number 15. Which can manipulate hits authority scores in a citation network, adding citation from low impact papers, creating a creating a hub citing many papers, increasing self citation, and linking to high impact journals. So again I am repeating, which can manipulate the hits authority score in a citation network. Okay, so increasing the self citation can be one thing, and creating a hub citing many papers. So option B as well as option D. Okay, hits authority can be manipulated by artificially creating strong hubs and self citation loop which inflate hub authority reinforcement. So option B as well as option C is the correct answer. Let's move on to the case number 4. An online forum ranks users based on reply interaction, forming a directed graph. Okay, online forum discussion, all these things are there. Let's move on to the question answer. In applying hits to a forum reply graph, what defines a hub user? Replying to many users, replying many replies, posting original content, or option D, having high engagement. So option A, B, C, or D. So option A here is the correct answer, because it is a online forum discussion. So replying to many users is the correct answer. Okay, so in hits, a hub is a node that points to many authorities. In forum, replying to many users, especially authoritative ones, make user a strong hub. So option A is the correct answer. Let's move on to the next question. Which network properties enhance PageRank convergence in a okay, just 1 minute. Yeah, PageRank convergence in a forum graph. High connectivity, presence of dangling nodes, damping factor less than 1, or uniform degree distribution. So high connectivity and damping factor less than 1. So it will help enhance the PageRank conversion. So option A as well as option C is the correct answer. High connectivity has faster mixing of rank. Damping factor less than 1 ensure irreducibility, aperiodicity, guaranteeing convergence. So option A as well as option C is the correct answer. In a forum graph, A replies to B, B C, B to D, C to D, D to A. What is the authority scores of D after hits iteration 1? Okay, initial score 1 before the normalization. Okay, so what is the authority score? So we have to do the authority score. So authority score will be based on the incoming links. Okay, so authority score we have to go for D. Okay, so D has 2 incoming links, B as well as C. So authority score will be 1 plus 1, that will be equal to 2. Okay, so 2 is the correct answer. So always remember this thing: authority means incoming, hub means outgoing. Okay, so that is you have to understand. Okay, authority, wherever authority is, you have to see the incoming links. Wherever there is hub score, you have to see the outgoing link. Okay, but hub score is decided only after the authority. So this you have to keep in mind. So option 2 is the correct answer. How does homophily from earlier weeks affect the hits in a forum? Increase hub score uniformly enhances authority score within community, reduces convergence speed, or has no effect. So here enhances the authority scores within community will be right answer, because whenever we are talking about homophily, we are talking about forming a strong community. Okay, so homophily causes users to interact more with the similar group, reinforcing hub authority relationship inside community, leading to cluster authority. So option B is the correct answer. Which strategy increases a user's page rank in a forum? Receiving replies from influential users, replying to many users, posting frequently, being cited by high page rank users. So here option, definitely option A is correct, and option D is correct, being cited by high page rank users. So option A as well as option D is the correct. Page rank increases when important user link reply to you not when you create many outgoing links. So option A as well as option D is the correct answer. Now case study 5, recommendation system. A recommendation system uses matrix operation to rank item based on user interactions. Okay, so all these things are there, I am not going. Let's move on to the question answer. In a user interaction mix, what does matrix multiplication with a vector represents? True interaction per users, weighted sum of item score, item popularity ranking, uses similarity scores. So here weighted sum of item score will be the answer. Okay, multiplying a user item by a score vector aggregate indicates a weighted sum producing new score. Example, predicted user preferences or item ranking. So option B is the correct answer. Let's move on to the next question. Which linear algebra operation are used in PageRank computation? Matrix multiplication, vector addition, matrix inversion, eigenvalue decomposition. So matrix multiplication and vector addition is correct, but you have also understand this eigenvalue decomposition. So A, B as well as D, because it will take the direction of largest eigenvalue or the first eigenvalue. So that is why convergence usually happens. So A, B as well as D is the correct answer. Okay. So PageRank repeatedly applies matrix vector multiplication. Vector addition arises from teleportation. PageRank vector is dominant eigenvector. So this you have to understand. Matrix inversion is not used in practice. So option A, B as well as D is the correct answer. Okay, yeah. So a matrix, this is the matrix. Okay, so 0.6, 0.4, that means this is the first row and this is the second row. Okay, so 0.6, 0.4, 0.3, 0.7, what is 1 cross 1 entry of A square? So very easy, just you have to multiply with same matrix, that is 0.6 and 0.3 and 0.4 and 0.7. So very easy, just multiply the matrix. How we will multiply the matrix? Matrix multiplication will be this to this and this to this. Okay, then this to this and this to this. Okay, so we only require the A11 entry, so we only require this. So just multiply this with this and you will get the answer. 0.6 into 0.6, 0.4 into 0.3, so that is 36 and 12. 0.48 is the answer. 0.480 is the answer because 3 decimal places is as in R. So very easy. Okay, and then why does repeated matrix multiplication converge in a page rank? The matrix is symmetric, the spectral radius is less than 1, the matrix is stochastic and irreducible, the matrix is diagonal. So option C is the correct answer. Matrix is stochastic and irreducible. So stochastic, irreducible and aperiodic matrix define the Markov chain ensuring convergence to a unique stationary distribution. So option C is the correct answer. Question number 25, which vector operations are used in hits update? Addition for score aggregation, scalar multiplication for normalization, dot product for similarity, cross product for ranking. So here it is option A as option B, that is addition for score aggregation and scalar multiplication for normalization. Okay, so option A as well as option B. So hits update add neighbor scores have authority and normalize via the scalar multiplication. No similarity or cross products are involved. So option A as well as option B is the correct answer. Now last case, that is network resilience analysis and network analysis resilience using iterative matrix operation to model information flow. Okay, so these are the things I am not discussing. Let's move on to the question answer. In a stochastic matrix A, what ensure convergence of the convergence of all eigenvalues are positive? The matrix is irreducible and aperiodic. The matrix is orthogonal. The matrix is rank 1. So option B is the correct answer. Okay, so that is matrix is irreducible and aperiodic. We have discussed it again and again. Irreducible, every state is reachable. Aperiodic, no fixed cycles. Okay, so this ensures convergence. Okay, so option B is the correct answer. Which factor affects the convergence speeds in a repeated matrix multiplication? Select that applies. Second largest eigenvalue magnitude, matrix size, initial vector choice, matrix sparsity. Which factor affects the convergence speed in repeated multiplication? Okay, so that will be A, C as well as D. That is second largest eigenvalue magnitude, initial vector choice, because first in a largest eigenvalue vector magnitude, that will give you the direction. Okay, but second largest eigenvalue magnitude, that will help you in normalization. Okay, and then initial vector choice and matrix sparsity. Okay, so second largest eigenvalue, the closer this to 1, the slower is the convergence. Initial vector choice, some initial vector aligns better with the dominant eigen vector, affecting how quickly convergence is reached. Matrix sparsity, sparse matrices allows faster computation per iteration and can influence the effective propagation, indirectly affecting the convergence speed. Okay, and matrix size only affects the computational cost per iteration, not the theoretical convergence rate. Okay, second largest eigenvector magnitude, SLEM, it determines how quickly repeated approach the stationary distribution. Okay, initial vector choice, if has more projection onto dominant vector, convergence is faster. Matrix sparsity, fewer non-zero zero matrices or entries means less computation per iteration and faster information propagates along the non-zero paths. And matrix sizes, larger matrices make more time to compute, but they don't change the number of iteration needed for convergence in theory. So option A, option C as well as option D is the correct answer. Okay, now let's move on to the next question. For a transition matrix, this is a transition matrix. What is the stationary distribution first component? Okay, so how we'll solve it? So this is the transition matrix. Transition matrix, it is actually the transpose of it. What we have learned the other thing. Okay, that is sum of column entries are 1, but here sum of row entries are 1. Okay, so just reverse, just transpose of it. Okay, so same thing. 0.6, 0.4 will give you 1 and 0.3, 0.7 will give you 1. So that is why it is a transition matrix. What is the stationary distribution first component? So how we can solve it? Let pi equals to x into 1 minus x. Okay, and solve, you have to solve this pi p into pi p equals to pi. Okay, so pi p equals to pi. When you will solve it, so we will take only the so let me just solve it. So x into 1 minus x, sorry, so x into 1 minus, this is x. Okay, x into 1 minus x. Okay, that will be equal to into, sorry, so that this we have to multiply with this. Okay, this we have to multiply with this. Okay, that will be equal to this only. Okay, that will be equal to pi only. So how we'll do it? So x, so we do this into this, right? So x into 0.6 and 1 minus x into 0.3, that will be equal to so this is the first element. So first element will be equal to first element of this, that is x. Okay, just solve it and we are getting x equals to 0.429. So 0.429 is the correct answer. That is the first component of the stationary distribution is 0.429. So that is the correct answer. So 0.429 is the correct answer. So what you have to remember? You have to remember this pi p equals to pi, and what is pi? Pi is nothing but x into 1 minus x. Okay, that you have to remember, and by this you can solve the first stationary distribution component. Okay, so option 0.429 is the correct answer. Now question number 29, in a resilience analysis by vector addition to compute Eigenvalues to combine influence from multiple sources to normalize score and to or to invert the matrix. So very easy, that is B. To combine influence from the multiple sources is the correct answer. Vector addition aggregates the incoming influence or flow from different neighbors, modeling how information or importance accumulate across the network. So option B is the correct answer. Now last question, which properties make a network resilient to disruptions in PageRank? High connectivity, low damping factor, presence of hubs, uniform degree distribution. So here it will be high connectivity and presence of hubs. Okay. So that will make a network resilient to disruption in the PageRank. Okay, resilient means it is resilient. It is resisting the disruption in PageRank. That is high connectivity and presence of hub. High connectivity, multiple paths ensure PageRank continues to flows even if some edges or nodes fail. Presence of hub acts as a central connector helping maintain rank propagation despite the disruption. Okay. High connectivity, it ensures alternative path exists for rank propagation. Hubs, central nodes distribute rank efficiently, and low damping factor and uniform distribution do not inherently improve the resilience. So option A as well as option C is the correct answer. Okay. So with this, I have ended the question answer session. Okay. Now we will see two of the quotes and then we will disperse the class. Okay. So just so let me share my entire screen. Yeah. So my entire screen has been shared. Let me hide this. So quotes for this class. So that is PageRank convergence analysis and visualization. So you can just see this. Let me open this also. Okay, so let me see. So what we will do, we will define the system parameter. We have 5 nodes. Okay, and then we will give the 0.2 initial rank, that is 0.2 to all those. Okay, and then what we will do, we will be applying the rules by this. A will be C by 3, B A plus C by 3 plus E by 2, C equals to B, D C by 3 plus E by 2, or E equals to D. Okay, by this we will update it and you will see the result. Okay, so this is the network. Okay, so A is connected to B, B is connected to C, C is connected to D, D is connected to E, E is connected to E is connected, or E is following D, E is following B also, and C is following B and C is following A. Okay, so this is the entire thing. Okay, so this is the entire thing. Now you can see after the first iteration, 0 iteration, all the rank are 0.2, 0.2, 0.2, 0.2, 0.2. After the first iteration, it is this 0.667, 0.22, 0.200, etc. Okay. After the 26 iteration, it is 0.908 this, and after the 30 iteration also this is. Okay. So you can see after like 26 iteration. Okay, let me just show you. After the these are all the page rank, how it is page rank for each node, how it is varying with iteration number. Okay, so at first 0 iteration, all the it's starting from 0.2 because 0.2 is our initial, but after 28 iteration or 26 iteration, you can see after 26 iteration it is converging to stable ranking, that is 0.908, 0.2725, 0.2730, and 0.1815. So okay, so after 30 iteration it is actually converging. Okay, and the converging actually start from 10 iteration. So 10 iteration, when you will see the 10th iteration or 11th iteration or 16 iteration, you can see there is not more change. Okay, there is not more change in the values. So that is how convergence of page rank occur in this network. Okay, in this network. Okay, so this is the first code, and second code, it is regarding the concept. So first is convergence in repeated matrix multiplication. So this is the vector 1, and the vectors actually converges after, you can say after seventh vector it is actually converging. Okay, so you can see in the graph. So initially this is the vector. Okay, initially this is the vector, it has three component, that is the blue component, orange component, and green component. So initially you can see different components. 0, we have highest blue component 1, and 0 0 for orange and this green component. But after, you can say, after this fifth iteration, it is almost all the component are converging to a stable thing. So this is convergence and repeated matrix multiplication. Okay. Now addition of two vector, this is the addition of two vector code. Okay, so what we getting, so big vector, it has magnitude this and angle this, small vector, it is magnitude this, resultant has magnitude this, okay, and angle this. So shift in angle is only 1.94 degree to the angle to the big vector. Okay, so resultant will always prefer the big vector over the small vector. So this is addition of vector. Okay, and then combination of two, we are getting this. Okay, so again this is the same thing. After many iteration, like 10th iteration, the stabilization of the ranks ultimately take place. You can see the concepts behind this. Okay, so these are the two codes. So by this I am ending the session for today. Unfortunately no one has joined it, so I request in the next class people to join it and we can discuss much better. Okay, so by that I am ending the session for today. We will meet on the next Tuesday, same time, 6 to 8 p.m. Okay, so bye.